Welcome all. Today I am going to solve a problem from abstract algebra. The problem is show that for every integer n, the number n raised to 33 minus n is divisible by 15. Here we want to prove that for every integer n, this number is divisible by the number 50. For that, let us take this number first. N raised to 33 minus n is equal to n into n raised to 32 minus 1. This number can be written in this form by taking n common. So we get n into n raised to 32 minus 1. Next, let us take the number 15 first. Let us take the number 15. 15 is equal to 3 into 5. 15 is equal to 3 into 5. 15 can be written in terms of 3 as well as 5. So we have to prove that for every integer n, this number or the number n raised to 33 minus n is divisible by 50. For that, it is enough to prove that 3 is divisible by this number and 5 is divisible by this number. We can at last say that 15 is divisible by n raised to 33 minus n. Once again, we can say that 3 is divisible by n raised to 33 minus n. 5 is divisible by n raised to 33 minus n. At last, we can say that 15 is divisible by n raised to 33 minus n. So, if 3 divides n or n is divisible by 3, if 3 divides n or n is divisible by 3, then 3 divides n into n raised to 32 minus 1. Because n is the multiple of this number or this number is multiple of n. So we can write if 3 divides n, then 3 divides n into n raised to 32 minus 1. Let us assume that 3 does not divide n. Then by Fermat's little theorem, we have if a belongs to z and p be a prime number not dividing a, then a raised to p minus 1 congruent to 1 mod p. That is, if p be a prime number which does not divide the number a, if a belongs to z, p be any prime number which is not dividing a, then a raised to p minus 1 congruent to 1 mod p. Here, let us take the number p is equal to 3 and a is equal to n. P is a prime number. That is p is equal to 3, which is not dividing a. So here we can apply this statement in this condition. If 3 does not divide n, then we can write n raised to 3 minus 1 congruent to 1 mod 3. A raised to p minus 1 congruent to 1 mod p. Here p is equal to 3 and a is equal to n. So we can say that n raised to 3 minus 1 congruent to 1 mod 3. By Fermat's little theorem, we have this statement and apply this format. We can write this. N raised to 3 minus 1 congruent to 1 mod 3. 3 minus 1 is 2. So n square congruent to 1 mod 3. When we multiply the power by 16, we get in this form n square the whole raised to 16 congruent to 1 raised to 16 mod 3. So 16 into 2 is 32. So n raised to 32 congruent to 1 mod 3. Or we can write n raised to 32 minus 1 congruent to 0 mod 3. Once again, n raised to 32 minus 1 congruent to 0 mod 3. At last, we can have 3 divides n raised to 32 minus 1. 3 divides n raised to 32 minus 1. We can say that if 3 divides n raised to 32 minus 1, 3 divides n into n raised to 32 minus 1, which is 3 divides n raised to 33 minus n. Let us take this as equation number 1. After taking that number as equation number 1, now let us take the number 5. If 5 divides n, then 5 divides n into n raised to 32 minus 1. If 5 divides n, 5 divides n or n is divisible by the number 5, then 5 divides n into n raised to 32 minus 1 because this number is multiple of n. So 5 divides n into n raised to 32 minus 1. If 5 does not divide a, let us assume that 5 does not divide a, then by Fermat's little theorem, if 5 does not divide a, then by Fermat's little theorem, we have if a belongs to z and p be a prime number not dividing a, then a raised to p minus 1 congruent to 1 mod p. That is, p be any prime number which is not dividing a, then the Fermat's little theorem states this: a raised to p minus 1 congruent to 1 mod p. Here we can take 5 does not divide a. We have assumed that 5 does not divide n. Then a raised to p minus 1 congruent to 1 mod p. Here p is equal to 1 and a is equal to n. P is equal to 5 and a is equal to n. P is a prime number, that is 5 is a prime number which is not dividing n. 5 is a prime number not dividing n. Then we can apply this. So a raised to p minus 1, n raised to 5 minus 1 because a is n and p is 5. P minus 1, 5 minus 1 congruent to 1 mod 5. N raised to 5 minus 1 congruent to 1 mod 5. Here n is equal to a or a is equal to n and p is equal to 5. So we can write this one. 5 minus 1 is 4. So n raised to 4 congruent to 1 raised to 4 mod 5. N raised to 4 congruent to 1 mod 5. Multiplying the power by 8, we get n raised to 4 the whole raised to 8 congruent to 1 raised to 8 mod 5. We are here multiplying the power 8 in both LHS and RHS. So 8 into 4 is 32. So n raised to 32 congruent to 1 mod 5. Or we can write n raised to 32 minus 1 congruent to 0 mod 5. N raised to 32 minus 1 congruent to 0 mod 5. So at last we can have 5 divides n raised to 32 minus 1. 5 divides n raised to 32 minus 1, or this number is divisible by 5. N raised to 32 minus 1 is divisible by 5. Also 5 divides n into n raised to 32 minus 1. 5 divides n into n raised to 32 minus 1. This number is divisible by 5. This number is divisible by 5. Let us take this equation as equation number 2. From equation number 1 and equation number 2, we can write 3 into 5 divides n into n raised to 32 minus 1. So 5 into 3 is 15. 15 divides n raised to 33 minus n. Multiplying n inside the bracket, we will get n raised to 33 minus n. Here is the proof for every integer n, the number n raised to 33 minus n is divisible by the number 15. Or we can say that 15 divides n raised to 33 minus n. I hope this question is clear. Thank you.